So, in the previous class we talked about how we can try to model a hovering rotor, and in the earlier introductory video we saw the kind of your flow field that a rotor generates. So, you have tip vortices getting shed and they come in a helical shape. So, we said all that complexity is fine, but we can model that with the simplest possible theory called momentum theory, where we assume that the flow actually is nicely streamlined in a particular manner, going all straight through the way you see here in the sketch here. And based on that we then said, okay, let us model a hovering rotor. So, even though I have drawn a picture of a helicopter, but it could be any rotor, it could be a rotor for a multicopter, it could be a rotor for a hexacopter, it could be rotor for a conventional helicopter based unmanned helicopter design, or it could be even a optionally pilotable large helicopter. So, next week I am going to Bangalore to discuss this project with HAL, where we are proposing that it is high time that HAL starts converting their manned aerial vehicles into optionally pilotable aerial vehicles. So, in Kanpur we have this Dornier aircraft that gets made. It is a fairly I would say capable aircraft, and the entire manufacturing is done in Kanpur. So, one can imagine that we can easily convert that into a cargo carrying long range drone, drone airplane. So, Air Force is looking for solutions which would actually allow them to transport 500 kg over 1000 kilometer. So, Dornier can do 1500 kg over 500 kilometer, or some 600 odd kgs for almost 1200 or 1500 kilometers, something like that. So, you do not have to make a new UAV from scratch. I can just take the existing craft, it has fair amount of cargo space, I can take out the furniture and everything extra which is not required anymore, and I can try to convert that. So, anyway, so bottom line being that when I talk about unmanned aerial vehicles, you would soon see full scale aerial vehicles becoming unmanned or uncrewed as we call it. So, this is the simplest model where I look at a hovering rotor and we say that my rotor is acting like an actuator disc, which is imparting some small velocity to air, and while my actuator is doing some work, air is in turn giving it some reaction, and as a result of that my rotor actually generates lift or thrust for that matter, which balances my weight and therefore, my system can hover. And we said that we can, with these assumptions in place, we can use the fundamental conservation laws, where we say mass conservation, that is mass entering or mass being pushed through the rotor disc, would the same mass will flow out of the entire control volume that we defined. So, that is my mass conservation. Then we do momentum conservation, where we say, okay, my reaction force which is thrust is equal to m dot v, vi rather, and during this generation of thrust there is some amount of work that rotor is doing on air, which is given by T into Vi, and this work done would cause change in my kinetic energy of air going through the rotor disc, and that actually we normal kinetic energy is half mv square, where v is your velocity. So, here because it is a rate of change of work done or rate of change of kinetic energy. So, it is basically a power term which is half m dot w square, because it is not a constant mass, it is a mass that is flowing through it. So, by the law of conservation of energy, we end up with this expression where my work done should be equal to change in kinetic energy. So, these are the three key equations which I have at my disposal. Now, if I use equation 2 and 3, let us see, which means I will substitute for T as, so use 2 and 3, what do we have? It gives me T is equal to m dot v. So, I will put that over here. So, m dot v vi, it becomes m dot vi square equals to half m dot w square. So, m dot goes off, and oh sorry, this is wrong, actually this is not m dot v, it is m dot w. Okay. This is a mistake I made. Let me just erase this term, because finally the this is from the previous time. So, it is already written on that. So, this actually is incorrect, it is m w I, because we are looking at the momentum leaving the system. Why? You see, what is the momentum which is entering the system is from here, it is 0, because we are considering this point as far upstream of the rotor disc. So, therefore, there is no momentum entering, but what is leaving the system is actually W. So, my change of momentum is happening from MWI minus M to 0. So, it is MWI and not that. So, d by dt of MWI is basically m dot Wi, not Vi. So, that is a small mistake there. This is correct actually. Yeah. So, m dot Wi. So, m dot Vi into m dot Wi, right, that is what you will end up getting, because this m dot Wi and T into Vi was already there. So, that is how it is. So, now this Wi will cancel this and we end up with Vi equals to W by 2 or W equals to twice of Vi. Okay. So, what is this information now? What is my W? What is the name for this? Wake velocity. So, it is my downwards velocity or wake velocity. So, this is the same velocity if you turn on a fan, the wind that you experience under the fan, that is the same speed. So, W is equal to twice of Vi, and Vi is my induced velocity. So, my wake speed far downstream of the rotor is twice of the velocity which my rotor has induced. Okay. So, this is one new information, I will call it 4 maybe, then let us move on and see what else we can do from this. So, if I use this information in my equation number 1. Okay. So, equation number 1 is about rho A Vi and rho A 3 W. So, rho is same in both the sides of the equation. So, we see A Vi equal to A 3 W. Okay. So, we have A Vi equals to A 3 W, and now we know that W is twice of Vi. So, A Vi equals to A 3 into twice of Vi, right. So, this Vi gets cancelled and it tells me that my A 3 or A infinity whatever, maybe I call it A 3 here. So, A 3 equals to half of A. Okay, so, why do I need to care about this? Well, this sort of allows me to verify this theory by experiments, which means I can put a probe in my rotor wake far downstream and try to measure my wake velocity. See, if you are outside the, if I go back here, if I am outside this boundary of the slipstream, this control volume, what speed I am going to experience? 0, right. So, outside this there is no flow. So, it is like, I mean, you have a fan over your head and you keep experiencing it, but you go away from it, you will not experience any flow. But in a room it is a closed environment, so finally air circulates, so you experience it in many places. But if you keep it in a more open kind of environment, say I keep a horizontal fan in a very open area, big horizontal fan. So, the moment I am in the wake, I will see the flow, the moment I go away, I will not experience any flow, right. So, that is the point. So, I will put a probe which will measure this, and through that I can actually measure this with some degree of accuracy, or I can use more advanced instruments like PIV, particle image velocimetry. I can shine a laser sheet and put some particles, and by looking at how the flow field is, I will be able to get the velocity field end for the entire area. So, with that I can also quantify how my wake looks like. Okay. So, if I do that and make measurements, it turns out. So, what this tells me that, I mean, my A is pi r square by 2, which means, and this is pi r 3 square, sorry, not A r 3, pi r 3, pi r square by 2, which means this r 3 is r divided by root 2, which is 0.707 times r. So, it is telling me that far downstream my disc area, if I cut through my wake using a horizontal plane, that has an radius of almost 70% of my rotor radius or 71%. So, if I do this measurement experimentally, experimental value comes out to be experiment gives me this r. So, I will call it small r 3 by r to be almost 78%. So, my theory is giving me 71% and my actual number is giving me 78%. So, that is merely a difference of 10%, right. So, it is not so bad, it is a very simple theory, it kind of removes every possible complexity, but even with that I get a fairly reasonable answer, only off by 10%. Yeah, so, this is one verification. Yeah, so, now we go back and try to get my thrust equation T equals to m dot W. M dot is what? Rho A into V I, W is twice of V I, right, which means now I can write the expression of this V I in terms of my thrust. And you will not believe this is a very important equation, very simple, but very important and very powerful equation. So, this tells me that my induced velocity depends on thrust and rotor disk area, right. So, directly if I increase my thrust, my induced velocity will change. Now, question is what is my thrust here? Do I know this? Right, because for a hovering rotor. So, I am trying to find out how much my rotor has to induce the velocity when my quadcopter is in hovering flight, right. So, now my T equals to W for hover if my UAV is a single rotor UAV, right, because only one rotor is producing all the thrust which is balancing my weight. If my for a multi rotor system, with n r being number of rotors, right. If that is the case, then my relationship would be W would be equal to n r times T. All of you understand, right. We will at this point also introduce a new term called disk loading. dl as T over A. So, the unit would be Newton per meter square or pound per feet square. So, this thrust per unit area. So, if I insert this into my induced velocity formula, my V I can be written as square root of 1 by 2 rho into disk loading, and this formula is right now for hover condition, and apart from hover you can have climbing condition, you can have forward flight condition for your rotor, So, depending on all those other conditions, your induced velocity is going to change, but hover condition is very unique. Hover is when my thrust is exactly equal to my weight, thrust from all the rotors. So, to differentiate that, we would give it a name called V subscript h. So, this we call as hover induced velocity. Yeah. So, we call this as hover induced velocity or induced velocity in hover. So, what is the use of this thing called disk loading? We will see this actually happens to be a very important parameter, especially in deciding your design. In your rotor design, it becomes a very important parameter, similar to what we have in our fixed wing. In fixed wing, remember we had W by S, okay, which is wing loading. Okay. So, W by S we had, which we called as wing loading. And what was that? It was basically my weight or my lift basically divided by my area, okay, total area of the wing. So, that becomes my wing loading, and wing loading directly governs your performance and your entire design of a fixed wing UAV. Likewise, here your disk loading will govern the design of a rotary wing UAV. So, this disk loading, this governs performance in hover and overall design. How? Let us try to see. So, that we can look at power in terms of this, but maybe okay. So, disk loading, maybe I will give you some number also for this. As an engineer, it is very important to have a feel for numbers, like how should the disk loading look like, what would actually be a meaningful number, because otherwise if you do not have a sense of that, if you make a mistake and you get wrong answer, you will not be able to know that it is a wrong answer. Okay. So, if somebody gets a parameter for disk loading which is unrealistic, it will immediately indicate to him that there is some mistake in calculation, assumptions, etc. So, disk loading I will give you in the both the units. So, because of my training in US, I am more familiar with the number in terms of pound per feet square. So, in US they still use FPS units, which may be a surprise for many of you. So, I would expect that or rather I expected that nobody in the world was any more using imperial units. So, nobody talks about miles, nobody talks about foot or pound, and the worst case thing something called slug. Have you heard what is slug? It is unit of mass in FPS unit. So, there is something called slug, pound and all that. So, that is what I had to learn. So, disk loading for UAVs would probably range for from maybe 2 pound per feet square to, well, to larger size systems would actually have higher value, which is quite obvious also, because you see this loading is thrust per unit area. So, what is the unit of thrust? Let me first write this number down, then we will come back to that. So, to maybe 12 pound per feet square or something. Okay. Same thing in newtons per meter square would be probably, say, I am not exactly converting, I am just giving you approximate number, 100 Newton per meter square. Actually, for small UVs it is even less, actually it is not even 100, it is like 60, 70. Okay. 70. Yeah, so 70 Newton per meter square to some big number like 500 Newton per meter square. So, I am not doing a direct conversion. Okay. It is not like I have converted from pound per feet square to newtons exactly. I am just giving you ballpark numbers, round numbers which are easy to remember, instead of giving it in some fractional form. So, small UAVs you will see they will probably have disk loading of this kind of number, while larger UAVs have this larger number. Why? Why? Because this disk loading is a dimensional parameter, it is not non-dimensional. If you look at non-dimensional things, then it does not change with scale of or size of the system. So, we will also define some non-dimensional parameters very shortly, and those parameters would remain exactly same whether my UAV is of this size or of very large size.
So shouldn't it be pound force instead of just pound, because
Pound is only pound. There is nothing called pound force here. Pound is unit of your weight or newtons. It's equivalent to newtons basically. Yes, it is not your
What is mass?
slug.
Oh.
That's what I was talking about. Okay. So slug multiplied with your 32.5 or 15 feet per second square converts it into pound. Okay. Yeah. So there is nothing called pound force. Pound is already unit of force. Okay. So right. So these are the numbers. Now if you look at disk loading is thrust per unit area, thrust is force, force is mass into acceleration. So mass is your density. So if we try to convert, so right, so maybe I can look at this as thrust per unit area. So force is Newton, which is kilogram meter, okay, per second square, okay, and then divided by meter square. Okay. So this meter goes away. Kilogram is mass, which I can write as a density, which is a material property. So density I will consider it as a constant for across all systems. So density into volume, which is meter cubed, okay, divided by meter second square, right. So this becomes meter square. So you see this is going to scale. If I say the density is same, it is going to scale up with, I mean, the dimension, okay, because time scale also does not make any difference. It is same for everything, whether it is bigger system or smaller system. But what the moment my dimension changes, okay, meter means my dimension. If my length dimension changes, I would expect my disk loading to sort of increase with dimension, right. So that is why my disk loading is higher for larger systems compared to smaller crafts. Okay. So this is just something I just wanted to give you a hint of. It is not rigorous or critical, but just to give you why it is going to change with. Okay. So this is my disk loading, and how does it impact my performance. So now we will try to get my power in terms of this induced velocity. Yeah. So power for hover, power P was T into Vi, okay, and we know already Vi in terms of my T. So T into root of T by 2 rho A, which means my power is T to the power 3 by 2 by, so that is my power. If you want, you can even write this as T by root 2 rho into square root of disk loading, and we know T is same as W. Okay. So in effect, for any hovering rotor, I can immediately find out the power consumed by that, right. And but the question is that, I mean, how accurate is this power? So before we answer that part, we need to look at other thing is, of course, that I see that my P is directly proportional to square root of disk loading. What does this tell me? If my disk loading is higher, would my rotor consume more power or less power? Everybody agrees to this? And so ideally, if I want my rotor to consume less power, my UAV to consume less power, my quadcopter to consume less power, I would want it to have smaller disk loading. But question is that how do I reduce my disk loading? By increasing area, right, because my weight is not going to change. Assuming that my propeller, if I increase the propeller slightly, the difference in my propeller weight will be few grams only, so which is not going to change things dramatically. So if I am making a quadcopter and it weighs 4 kilos, for example, okay, if I use a 16-inch propeller versus a 20-inch propeller, which one will consume less power? 20-inch propeller. All of you agree, right? So that is the, and it is a very important information. So between 16 to 20 inches it may not make a huge difference, but if you change from 16 to 32 inches for example, okay, double, right, it is a very dramatic change.
Number of rotors. No?
That we are not considering here at all, okay, because we only know A. What is my A? It is area of the disc. So this theory right now does not have any sense of number of blades in a rotor. Okay. So whether my propeller has 2 blades or 3 blades or 4 blades, it does not care. How does that impact my power? We will see in a moment, okay. But before that let us try to absorb this completely. So if I double up my radius from 16 inches to say 32 inches, how would it affect my power? Let's check it very quickly, right. Okay. My area would change by how much? If I double my radius? 4 times, right, which means my power will change by half. Like that is magic, right. How did this happen actually? So everything remains same, I just put a larger propeller, double size, and my power will come down by half. So my drone can technically, theoretically fly for double the time. So if my drone with 16-inch propeller was flying for 30 minutes, if I am not increasing the weight significantly by putting this larger propeller, it will fly for exactly double the time. Okay. So that is a very simple thing to understand from this momentum theory, okay. And this is something which people do not understand or realize that readily. Okay. So fine, so let us discuss this further. Fine. So my disk loading, we can say that lower disk loading means less power consumption, right. Which means larger rotors are preferred if I am only worried about my power consumption. But larger means, I mean, how large? Why use 32? I mean, I can use 64-inch propeller. What is the problem? Right. So eventually my propeller will start becoming heavier, and when I go to larger scales, if I am looking at a conventional optionally palatable helicopter, right, I mean I am looking at say ALH Dhruv, and I change the radius from whatever 5 meters, 6 meter this radius is to 10 meters, the blade will become very heavy and very long. Long and slender means it will start to droop. So and my hub may have to be made stronger, larger to support the all this. So it will eventually start making my whole system heavy, which means my W is no longer constant. When W is no longer constant, then my power will also increase because of that. Okay. And therefore, I mean you can only go to a larger size as per whatever you are allowed for. Sometimes, I mean from a designer's point of view, your user may put a constraint. Yeah, so I mean defense side people talk about, I mean the dimension of the UAV in deployed condition and in the stored condition, which means, I mean they may say, okay, I mean your logistic drone should not become so big that I cannot fit it in behind a particular truck. So they may say, okay, this is the dimension inside which I should be able to store it. So I want to transport 3 of these drones in a particular truck which say army owns. Navy can come back and say, okay, because I have to operate from ship decks, so in the deployed condition it should not have more footprint than this, and in the stored condition it should be only carrying 1/10 of the space. So make it foldable or something, right. So the people would put constraints, so that also will become an important parameter for you to look at. So I cannot arbitrarily keep on increasing my size, but wherever I have chance I would want that, because less power consumption means better flight time and better aerodynamic efficiency. Now at this point I will ask one question. Let us say I want to design a manned helicopter or even a say drone helicopter which will now do a rescue mission. So, this is a helicopter which will fly in maybe flooded areas, okay, because we see so many. I mean, this year, I mean, our rains have been really crazy, and we have seen so many instances of flooding, your landslides, all kinds of problems. And that is where, I mean, helicopters come to rescue. So, you have to go and do this kind of search and rescue mission in, say, deep sea. Would you prefer a larger rotor size or a smaller rotor size, and why? Question is to design a search and rescue unmanned helicopter do we prefer larger rotor or smaller rotor, and why also? Saying larger, why? Say smaller, also why? Let us not worry about the weight per se. Okay. Let us.
Larger than your loading is lower, so means your power consumption is lower, you can hover for longer.
I mean, I am not thinking from that perspective at all right now.
Because the larger area it is, going to sweep under it as well. So people in the sea will be not able to be rescued.
Okay, so for same problem, both of you are proposing from different perspectives. Okay. So he is saying that, I mean, I should use smaller one because then, I mean, my area where the downwash is going to be smaller. Okay. You are saying I will use a larger one because then my flight time will be more. Okay. Well, I mean, both of them have their own pros and cons, but one perspective could also be that, I mean, if I use larger rotor, my downwash speed is also less. So, you are trying to rescue somebody in water, in a water body, and how do you rescue him? Okay. You will have to probably throw a live vest or throw that flotation device, right, something like that which he will try to grab onto. So, you throw this and there is a lot of air blowing onto it. What is the chances of guy catching that actually, right? So, if you think from that perspective, I mean, I would ideally want something rotor system which will have lower downwash. Okay. So, lower downwash means larger radius and lower disk loading. So, this is one way of thinking. So, I am just trying to highlight how something as simple as momentum theory can help you make very important design choices. So, these are just theoretical ideas, but in real world, I mean, you actually have to cater to these things. So, even without, I mean, getting into too much of detailed calculation, doing this simulation, CFD, this, that, I mean, I am able to understand and think about so many things very easily. I mean, you are trying to do mission in snowy areas, okay, with a large heli, okay, and when there is fresh snowfall, the snow is very loose. So, higher downwash can actually create a phenomena called whiteout. If you are doing similar operations in sandy environment, in deserts, it can create a scenario called brownout. What happens in these scenarios? The dust around you or snow around you will get thrown up when the helicopter is coming to land, and it would create this entire screen of brown or white. So, the person who is operating the craft, for the pilot, it becomes impossible to navigate and get the sense of depth. So, the screen of this brown dust or your white snow can really make landing very tricky and can cause, and it had actually caused many accidents, especially in Afghanistan operation for US Army helicopters. And as a consequence, I mean, they actually launched a study on this, and there were some projects which some of my friends worked on to study this brownout phenomena, and it is directly related to your downwash. So, they were looking at what could be done to mitigate this, what could be done to improve the visibility, how would pilot maneuver the craft to ensure that it does not actually enter brownout or whiteout scenarios. Okay. Okay, so now the fundamental question, we got this formula for power, which is nice bit of formula. How accurate is this formula? So, what I will do is that I will try to plot this. Yeah. So, you could imagine this graph would look p to the power 3 by 2, that kind of thing, and this we will call as ideal power. Now, if I compare, so my y axis is power, my x axis is thrust. So, I am trying to plot how my power varies with thrust, this same formula I am just trying to plot. Now, question is that, I mean, if I compare that with my experimental measurements, what would you expect? Are they going to match, not match, good match, bad match? What is your expectation?
It might follow same trend, but high.
The power will be high.
Yeah.
This formula is high or experiment is high?
Experimental support.
Experiment is high. Why?
Value like density vary and.
No, I mean I can model same density. So, what do you expect the power in real world to be? Less than this power? More than this power?
So more than this because
Why more?
we have made some assumptions while starting.
Right. So, we have ignored some losses. Right. So, ideal theory would not account for all the losses. So, my measurement should be higher, and that is what it is. So, experimental measurement would probably look, yeah, which means, so why I have marked experimental measurement with symbols? Because you can only make discrete measurements. So, something very important when you make any presentation, when you do your research, you normally report your experimental findings through symbols, because they are discrete, they are not continuous, and simulations exact formulas can be plotted as solid lines, because that I can plot at any number of points I want, continuous. So, there is some difference, and this will be my experiment. So, this is ideal because it does not account for any viscous effects. No viscous effects are considered in this. Okay. That is why this kind of difference is there. Yeah. And why this gap is there, and this gap you see actually grows at higher value of thrust. So, we will try to understand both of this in a minute, but before that we will define some new non-dimensional quantities, because with that we will be able to explain some of these things in a better manner. Okay. So, difference is clearly because we have ideal theory has not considered this. So, this P, so momentum theory power is also called ideal power, as opposed to real power, which I will actually experience. So, if I fly a quadcopter and measure its power, that is my real power, as opposed to what this formula is giving, and they are off. But what do I need to do to fix this gap? Yeah, that we will see, but before that we will define some non-dimensional quantities. Which are of relevance to us. So, why do we non-dimensionalize things? What are the typical non-dimensional parameters we have been dealing with so far? Reynolds number, fine, yeah, Reynolds number, Mach number, but beyond that, lift, yeah, I mean CL, CD, all these are non-dimensional parameters, okay. Moment coefficient, lift coefficient, drag coefficient, yeah, so they are all there. So, why do we non-dimensionalize?
Comparison.
Yeah, so it actually removes the effect of size and scale. So, scaling effects are taken away from that. So, what we do is that, I mean, in aircraft world we would normally non-dimensionalize or divide things either with chord or with span, those are two length dimensions. For helicopters we again do similar thing, mostly we divide with radius, sometimes we may divide with chord if I am measuring something along the chord. Otherwise, most of the times all dimensions, length dimensions will be divided by r, all speed dimensions will be divided by rotor tip speed, which is omega into r, because omega is constant for helicopter kind of things, single rotor systems, or even things which are flying with variable pitch. For multicopters, your omega is not constant, but at hover, point of hover, your omega will be one value. So, I can use that as a nominal value to divide things. So, my nominal tip speed will be again constant there. So, based on that we will divide now or define some new parameters called thrust coefficient given as Ct. Well, we have seen something like this in the propellers also, but it is defined slightly differently here. But here it is, yeah, thrust coefficient is defined slightly differently, but yeah. So, here my thrust coefficient is T by rho a omega r whole square. Okay. For propellers, it is divided or rather defined with half also there, or with slight differences actually. Okay. So, there are slight difference in that. It is not defined in terms of my tip speed. So, what is my omega r? Omega r is my rotor tip speed and my omega is my rotor angular speed in radians per second. So, Ct is T by rho a omega r whole square, and typical value of Ct would be going from 0.004 to 0.014. Okay, let me write this more clearly. Okay. And this is not so dependent on scale. Even for small propellers which you would be probably putting on multicopters, you will find that the Ct of that would easily be of the order of 0.01, okay, on the higher side. Then we have similarly power coefficient given by Cp, P divided by rho a, now omega r whole cubed. So, of 2, now there is 3. Based on this, I can also define another parameter called torque coefficient. Cq. How do I get Cq? Let us see. My power can be written as torque into omega, right. So, here we use Q, not T, because T is already taken by thrust. So, torque is always given by Q in rotary wing world, Q into omega. So, if I now define Cq as Q divided by rho a omega r whole square into r, right. How? So, you can see the dimensions are, see, it is non-dimensional, which means my rho a into omega r whole square has same dimension as force. How do I know? Half rho A, half rho S into V square, my dynamic pressure. Okay. So, dynamic pressure has same unit as lift, right. So, it is the same unit, there is no half just there, that is the thing, and like that. So, if I use this Q equal to P by omega in the same expression, I can see for myself that my CQ and CP is same number. I can multiply omega top and bottom, you see, omega Q into omega and R into omega. So, this becomes cubed and this becomes P. So, CQ and CP in non-dimensional form is same information, as long as my omega is constant, or I choose a omega which is nominal omega. Okay. Okay, so, moving further on the non-dimensional side, we will define induced velocity based on induced velocity. Now, we will call induced inflow, which is now my non-dimensional induced velocity. So, we had Vi, for hover we called it Vh. Using this, we will define now new parameter called lambda I equals to lambda h, which will be given by Vi by, what do I divide with to non-dimensionalize this? Omega r, right, omega r, what r? Speed. If you divide speed by distance, it will give you a time dimension, it will not become non-dimensional. So, I have to divide speed by a speed dimension. So, speed is omega r. Okay. And so, for this lambda h, we have again a special name, we call this as hover induced inflow as expected, and the typical number for this is 0.03 to lambda h 0.08. Okay. So, this is a typical number that you would encounter, but how does this relate to say other non-dimensional parameters? We can look at that. So, this is all clear, fine. Yeah, so, let us move further. Okay. So, I have Vi equals to square root of T by 2 rho A. So, lambda I for hover lambda h can be given as Vi by omega r, which means it will be T by 2 rho A into omega r whole square, fine. I am just putting the value of Vi, and because everything is inside root. So, if I want to push omega r inside the root, I have to make it omega r whole square. So, now you see what is inside here, right. What is this? It is my CT definition. So, I see my lambda h is nice and simple and compact square root of CT by 2. And going by the same logic, if I now look at the parameter T to the power 3 by 2 by root 2 rho A, which is my power, and it is also T into my Vh for hover. So, using this to get Cp T to the power 3 by 2 by rho A omega r whole cubed and to root of 2 rho A. You can easily see T by rho A omega r whole square is Ct, and the remaining stuff is lambda h. Okay. So, you see root of t by 2 rho a is my V I, and that V I divided by omega r is my lambda I or lambda h. So, lambda h and the remaining thing is basically C t. So, this I can write it like that, or I can write it like C t to the power 3 by 2 by root 2. So, this is my C p. And this is still my ideal C p, because I have used my ideal power, momentum theory power to define this C p. So, this is one C p, otherwise I mean if I have real value of power, I will get the real C p. So, just like I mean there is ideal power and real power, I have ideal C p and real C p. Okay. So, ideal C p is equals to C t to the power 3 by 2 by root 2. Okay. And at this juncture we can define one more parameter which actually would sort of help us quantify the efficiency of a rotor, though it is not non-dimensional, but we will try to get something in the non-dimensional form also in a moment. So, we are defining power loading, a new parameter called power loading. Given by P L is thrust per unit power. Okay. So, the unit of this you can think of is pounds per HP, or I can say newtons per kilowatt or newtons per watt or something. So, if you go and look at data of propeller, performance data of propeller given by many manufacturers, popular manufacturers such as T Motors, or now in India you have Vector Techniques, and then there is people like Reflex Drive. So, there are many Indian manufacturers also who are now manufacturing motors and propellers. So, they will give you the performance data, where they will give you throttle versus thrust, throttle, RPM, thrust, torque, power and power loading, where they will simply at the top they will put grams per watt. Okay. So, there is so many grams of thrust per unit of watt. So, here instead of Newton I can say gram also. Okay. So, grams per watt for smaller propellers. If it becomes very large, then we will talk about newtons per kilowatt or kilonewtons per kilowatt, something like that. Okay. So, it is a dimensional thing, but it is basically measure of hovering efficiency. It says how much thrust we can produce for every watt of power spent, which means for a rotor propeller system to be more efficient, do you want this number to be higher or lower? It says how many grams of thrust can I produce for every watt of power? Higher value, right? Okay. So, for 1 watt if I produce 10 gram versus 15 gram, I would want 15 gram one, right, for that same amount of power, which means if I want 10 grams I will consume less power, right. So, higher power loading is desirable, because efficiency you always want higher. So, power loading is indicative of efficiency. but it is a dimensional thing. So, for smaller propellers again power loading may be a smaller number, for larger propellers it may be you get a higher number and so on. So, to be more realistic you should compare them at same disk loading to give you more fair comparison. Another interesting thing to observe here is that this power loading is basically, if I see my power loading is equals to T by P equals to T by T into Vi as per momentum theory, which means my power loading is 1 over Vi. It is a reciprocal of my induced velocity, which means if I minimize my induced velocity, I maximize my power loading. How do I minimize my induced velocity? By using a larger disk area for same weight, as long as my weight does not change much. Okay. So, this also is then proportional to square root of disk loading, because we saw Vi was proportional to disk loading square root. So, that is something which you also end up getting. So, we will summarize by saying that to maximize power loading, we try to minimize what? Induced velocity Vi, which can be achieved with larger disk area or larger rotor radius, fine. So, this is again a general indication. If I have choice to select between 16 inch versus 18 inch, I would always want to go for 18 inch for same pitch condition and everything. So, because 18 inch will always be more efficient compared to 16 inch. Nothing, I mean nothing can change that really. So, we will quickly define one final parameter also for efficiency. Okay, but before that I think I need to define the key difference between my Okay, so any questions up to this point? No, fine. Okay, so let us again move further. So, we come back to our power graph, which so this was my T to the power 3 by 2 graph, and then we said we have experimental measurements which would probably fit on some line like that. Okay. So, question is why do we have gap here, and this is P versus T, and other question is that how does this, why this gap grows. Okay. So, first question let us try to understand what is this difference here. So, this gap here, so I mean as per my momentum theory, if my rotor is not generating any thrust, what is the power? Okay. Now, I will give you a propeller and I will say you spin it up, but run it in such a way that it does not generate any thrust, it is generating 0 thrust. Would it consume, would it still consume any power, or it will not consume any power? Why? Why would it consume power?
Spinning also, so you need to give them some power to spin it.
Why? That's the question, why?
Friction in the air.
Friction in the air. What is the name for friction in the air?
Viscosity.
Viscosity.
Drag. Right. So your rotor has drag. So you have to overcome the drag. And momentum theory did not talk about drag anywhere. That rotor has, because there is no rotor, it's a disc. So what a disc will have drag for? So there is no drag there. So this part is called your P naught. It's called profile power, and that's primarily because of the drag. Okay. So this is P naught. So now if I add this P naught to my black line, so I'll try to draw something which is more or less. So let's say I just shifted this black line by adding this P naught into that. Doesn't match. So P naught, first of all I will indicate P naught is called profile power, which is power required to overcome rotor blade drag. But this is not enough for me to get the actual real power, and this offset is because my momentum theory assumes no viscosity. So, it does not account for my tip vortices. So, tip vortices will have its own loss by diminishing my lift near the rotor tip. It will also account for some amount of energy getting lost in the swirling this helical flow. So, all those losses are not accounted for. So, what we do is that we say now total power or my real power is consisting of this ideal power plus this. So, ideal power is also my induced power, power required purely to generate this induced velocity. So, this is the power which is required to generate thrust. The other part of the power is a loss, it does not contribute to my thrust, but this Pi is not, from my momentum theory, is not accurate enough. It does not account for some losses as a function of thrust. So, to correct that, we define a new parameter called kappa, and this kappa is called induced power factor. Induced power factor, and more often than not you take this value as 1.15. So, it is an empirical correction or correction based on experience better theories which account for all these things. So, with that, now if I put P naught and put this kappa, then my answer would actually match fairly well with the experiment. Okay. So, that is what my, so I can call this P real or P total or whatever, okay, because now my Pi is my ideal power or my induced power basically, okay, and P naught is my profile power. So, I will give you expressions for all these. So, yeah. So, this gives my total power, and I already know what is my induced power. Sorry, I go back. Okay. So, what is my induced power? T to the power 3 by 2 by, okay. So, I will multiply this with kappa, but what is my profile power? Right now, I do not have a way to calculate that using momentum theory, because momentum theory does not cover it. So, there are better theories like blade element theory, which we will cover next. Okay. So, blade element theory allows me to calculate this and evaluate this. So, I will sort of take a jump or leap and give you the formula beforehand. We will actually derive this formula later on, okay. But right now we will use that formula, and that formula actually looks like this: sigma CD naught by 8 into rho A omega r whole cubed. Rho A omega r whole cubed you are already familiar with, okay. CD naught also you are familiar with, it is my zero lift drag coefficient for an airfoil. So, the same thing which we had in my fixed wing also. we had CD naught and then we have CDI induced drag coefficient. So, CD naught is also known to you based on your airfoil. What we do not know is sigma. What is sigma? It is called solidity, and it is defined as blade area by disc area, which means what is my blade area? If I have NB number of blades and C into R, if a blade's geometry is rectangular. So, let us say my one blade looks like this. Okay, this is one blade, simple blade, rectangular. So, this is my C, this is my R. Okay. So, my blade area becomes C into R, okay. And there are NB number of blades. NB is number of blades in a rotor. So, this is my blade area. What is my disc area? Pi r square. So, if I use this, my sigma becomes NBC by pi r. It is called rotor solidity, and this number is typically of the order of 0.06 0.12 typically. I mean, if I have high solidity, I can, in some cases I may use large number of blades, then I mean my solidity could be higher. So, increasing number of blade will automatically increase your solidity. Okay. So, this is my rotor solidity or solidity of my rotor, and so with this included now, I get my real power, and I will define one final parameter called figure of merit Fm, which we will call as ideal power by real power. So, you can understand what it will be. It is Pi divided by kappa times Pi plus P naught. Okay. So, we will stop here. We will bring all these parameters into this formula and discuss this figure of merit a little bit more on Wednesday, okay, same time. So, I will send a mail confirming the time, and so it will be at 10:40 basically. Okay. So, stop here.